This map details the transition from the financial tier to the education and collective tier. In the previous chapters, agents operated on highly visible, verifiable records of truth. A stock price either moved or it didn't. Agent 28, the education intelligence agent, operates in the exact opposite environment. A learner's mind is completely invisible to the system. The agent cannot directly measure understanding. It is entirely restricted to observing external behavioral signals, a wrong answer on a quiz, a hesitation before clicking submit, or the specific time spent on a single code block. It is like trying to understand an entire room by peeking through a single keyhole. The system must deduce the student's full conceptual understanding from restricted, low-fidelity inputs. Unlike data analysis or code execution, educational AI must optimize an objective it can never directly measure. Traditional learning environments often deploy a strict linear sequence. All students encounter the exact same topics, in the exact same order, at the exact same pace, completely ignoring their varied prior knowledge. Standard conversational AI tutors attempt to fix this, but fall into a predictable trap. They optimize for speed and task completion rather than actual knowledge retention. They generate the answer so the user can quickly move on. A student interacting with these systems can easily pass an assessment today, but their recall of the underlying material rapidly decays within days. To build an effective tutor, we enforce pedagogical alignment. Every engineering decision is constrained by established learning science, designing specifically for durable knowledge acquisition rather than short-term task efficiency. The solution requires converting that restricted keyhole view into a dynamic mathematical probability cloud. For every individual skill in a curriculum, the agent establishes a belief state, a calculated probability of mastery ranging from 0 to 100%. This drives a continuous operational loop. Observe the student's behavior, plan the next most effective intervention, and act to deliver that specific content. By modeling education as a partially observable Markov decision process, the previously invisible human mind suddenly becomes mathematically and computationally actionable. This architecture diagram outlines the complete system loop. When a student first enters the platform, they present a cold start problem. The agent has zero interaction history and no reliable estimate of mastery. An adaptive diagnostic test seeds the initial belief state, identifying the student's level using a fraction of standard questions. Once initialized, the student model serves as the system's core memory, maintaining probability clouds for every concept. These probabilities update continuously based on new inputs. Crucially, the model accounts for human inconsistencies. A single correct answer might be a lucky guess, and a single wrong answer might be a careless slip. This technique, known as Bayesian knowledge tracing, transforms noisy, unreliable interactions into a stable mathematical belief of capability. With a quantified belief state, the routing engine takes over, deciding the exact instructional step to take next. This diagram illustrates the prerequisite constraint layer. Advanced skills remain locked until foundational competencies explicitly cross the mastery threshold. The agent then enters a ranking phase, evaluating available paths to find the node offering the highest expected learning gain. The ranking mathematically targets concepts situated just beyond the student's current ability level. Content too easy causes boredom. Content too hard causes overwhelm. By calculating this optimal gap, the system uses Vygotsky's zone of proximal development as a strict mathematical filter for dynamic curriculum generation. Even a perfect lesson is subject to human memory decay. The system schedules reviews at expanding intervals to interrupt the forgetting curve. When errors occur, the feedback layer engages to diagnose the underlying misconception. It utilizes a two-stage detection pipeline. It runs ultra-fast, rule-based checks for common errors first, reserving latency-heavy LLM processing for complex mistakes. But algorithms have limits, requiring a safety mechanism that escalates control directly to a human instructor. The agent monitors for specific triggers, repeated task failure, textual signs of distress, or high algorithmic uncertainty in the student model. True autonomy in an educational system requires knowing exactly when to stop optimizing and call for a human teacher. This code block executes the Bayesian update step. This architecture runs on concrete logic, not theoretical philosophy. The math inside these functions shifts the overall belief state up or down after a single user response, recalculating the posterior probability in milliseconds. During the initial cold start, this exact script handles the placement test logic, calculating the statistical uncertainty of the student's ability estimate. The placement loop iterates, delivering new questions until the standard error drops below the configured threshold, ensuring a highly confident starting position. The effectiveness of the AI tutor is completely dependent on these rigid, hard-coded item response theory mechanisms and pedagogical guardrails. The agent sees a cold environment of probability calculations and vector constraints, but translates that into a clean, actionable dashboard for the human instructor. In real-world deployments, this architecture successfully automates baseline placement and provides adaptive remediation, measurably improving assessment scores and course completion rates. However, it does not possess human empathy, nor does it have contextual judgment about a student's life outside the system. Because of this, the human checkpoint operates as a structural pillar of the product, not an afterthought or a temporary crutch. AI's highest educational purpose is absorbing the computational load of tracking hundreds of fine-grained competencies, so human teachers can focus entirely on human connection. Agent 28 successfully maps and plans instruction for a single, invisible mind, but an entirely different architecture is required when moving from modeling an individual to coordinating a group. Next, we examine Agent 29, the collective intelligence agent, and decode the strict mathematical consensus mechanisms required for multi-agent coordination. To inspect the Python repository and the mathematical models backing the education intelligence agent, see Chapter 15 of 30 Agents Every AI Engineer Must Build. Mastering single-agent cognition is the fundamental prerequisite for building collective intelligence. Subscribe to continue the build.